All right, people, welcome back. So we're going to talk about some fun consequences today of this new theorem we got, the fundamental theorem of line integrals. So first we need a little bit of jargon. So a closed curve is a path or curve in either the plane or in space or in some higher dimensional space that starts and ends at the same point. So the sort of layman's term for this is probably a loop, right? It's a path that is closed up, so it starts at some point, and when it ends, it comes back and ends at that same point. And so one of our first consequences of the fundamental theorem of line integrals is that if big F is a conservative vector field and C is one of these closed curves, then the line integral of big F along C must be 0. Why? Well, if C starts and ends at the same place, and if F is the gradient of some function little f, then we're just evaluating little f at these endpoints that are equal to each other. And so you're evaluating little f at the same 2 points of space and taking the difference. Well, those function values need to be the same then, so their difference must be 0. Okay. And so if you have some arbitrary vector field, this is the sort of more important consequence of this. If you have some arbitrary vector field, big F, that maybe you don't know if it's conservative or not. And if you have some closed curve of the plane or of space, wherever the vector field lives on, and the line integral of that vector field over that curve is not 0, then the vector field you started with is not conservative, right? This has to be, so all you need to exhibit is a particular closed curve, a loop, along which this vector field integrates to a number that is not 0. Then you will be able to determine that big F, the vector field you started with, is not conservative. So, okay, so that's a sort of a different technique than what we'd had before, just kind of like looking for a potential function, little f, and maybe not finding one or something. This technique might be a little bit more slick than that, but still it might be a stretch to sort of pull some of the closed curve out of thin air along which this vector field integrates to some number that's not 0, right? So if you try to cook up a closed curve where this vector field integrates to 0, you really can't conclude anything. That's just one particular example of a curve. So it really only works this way when you have one where the integral is not 0, that you can conclude that the vector field is not conservative. Okay. So, for example, like we saw, this vector field, big F, is minus y in the first component and x in the second one. In the last example of section 16.2, I think it was the last example, we integrated this vector field along the unit circle, and we got, I think the number was 2 pi at the end, which is definitely not 0. So that's yet another way to exhibit that this vector field is not conservative. Okay, so now let's just consider some vector fields in the plane, because the next thing that's coming up is kind of just about those. So we can write one of these as big F of xy equals to p of xy in the first component and q of xy in the second component, where p and q are scalar valued functions of 2 variables each. So if this vector field, big F, is conservative, then it needs to equal to the gradient of some function, little f, right? And this is just the definition. And what does this mean then? That if we have p here and q here, that the partial derivative of little f with respect to x needs to be that first function, p of xy. And the partial derivative of f with respect to y needs to be that second function, q of xy. Okay, that's nice. So now let's take some more derivatives. Let's take some second derivatives here. So we'll get, if we take the partial derivative of f first with respect to x and then with respect to y, that's like the same thing as taking the partial derivative of p with respect to y. And if we take the partial derivative of f first with respect to y and then with respect to x, we get just the first partial derivative of q with respect to x. Okay. But if those derivatives here are continuous, then we get to apply the, Clairaut's theorem, otherwise known as equality of mixed partials, to say that the partial derivative of p with respect to y equals to the partial derivative of q with respect to x. Ah, very nice. So now we've just shown that if big F equals to, say, p in the first component and q in the second component, and if p and q have continuous partial derivatives, so we can apply the second partial the equality of mixed partials for some potential function little f, and if the partial derivative of p with respect to y does not equal to the partial derivative of q with respect to x, then the vector field f that we started with is not conservative. In particular, there cannot be one of those potential functions little f. Because otherwise, what we showed on the last slide would have had to have been true, and these would have had to have been equal. So this is a really clever way to show that some vector field on the plane is not conservative. So again, let's apply it to our favorite example now of a non-conservative vector field. Big F of xy is minus y in the first component and x in the second. So p of xy is minus y and q of xy is x. So the partial derivative of p with respect to y is minus 1. But the partial derivative of q with respect to x is plus 1. These two are not equal. So our original vector field, big F, is not conservative. I'd say this is probably the slickest way to show that that vector field is not conservative. So that's kind of a moral takeaway about this one. All right. So then let's see one more example, I think, here. So we'll consider the vector field big F of xy, which in the first component equals to y squared plus e to the x, and in the second component equals to 2 times y times x. Okay. And let's notice that if we try to show that this is not conservative, we don't really get off the ground. So we take that the partial derivative of p with respect to y is 2y, and the partial derivative of q with respect to x is also 2y. Now, we don't learn anything here then. We suspect that maybe f might be conservative because of this, but the implication does not work that way. So we cannot conclude that yet. Now, I will say that that comes with a kind of a big asterisk on it. So if our vector field has that its domain is all of the plane, so there's no little like holes in the domain or anything, then that converse of consequence 2 will hold, so that we can use this equality to imply that f is in fact conservative. However, we have not really learned all the details of that, and we aren't going to have time for it in this sort of slightly shortened course that we're running on. So we will just go ahead and show that big F is conservative the old-fashioned way, I guess, by exhibiting a potential function, little f, whose gradient is big F. So let's remind ourselves how that works. It's kind of fun. Remember that if that's the case, then we must have that function, little f, his partial derivative with respect to x, needs to equal to that first component of the vector field, which was y squared plus e to the x. So we can just integrate this expression now with respect to x and get some candidate for the function little f. So this goes just like it did in the talk about section, was it 16.2, I want to say? So we'll have here, by integrating with respect to x, we'll get y squared times x plus e to the x, and then plus some function that's just of the other variable y, right? This kind of same conversation from before. Okay, so now here's our good candidate for a potential function, little f. So we'll also need, though, that the partial derivative of this little f with respect to y needs to be the second component of that vector field, which was 2yx. Notice that if we take this one we have here and take its partial derivative with respect to y, we've got that already, right? So we don't really need this extra function g of y here. In fact, that would just get in the way. So really, we just need that g of y is some constant function. And we're allowed to pick any constant function we like. So my favorite one is the constant function that's everywhere equal to 0. Okay, so we'll pick that one. And that leaves us with our function little f of xy can be just y squared times x plus e to the x. So now we've got that potential function for big F. And we can do line integrals of big F now over any curve that we like by just evaluating this function. So let's suppose that we're given the curve C, which is the straight line segment that starts at the point 2, 1 and ends at the point 4, 0. Now I know you might be scared that you have to parameterize this line segment, right? To do a line integral of some vector field over this line segment, you might have to parameterize it. But the fundamental theorem of line integrals comes to our rescue here because we have exhibited the vector field in question to be a conservative one. It is the gradient of this function here. So all we have to do is evaluate the function little f at the endpoints of the curve. And those are 4, 0 is the end and 2, 1 is the start. So let's evaluate our function there. We get what? 0 squared times 4 plus e to the 4th minus 1 squared times 2 plus e squared. And so what do we get? This first term is 0, and we have e to the 4th minus 2 minus e squared. Looks pretty good. All right, and so that's all for the fundamental theorem of line integrals. It's a pretty fun one, and it gets some higher dimensional analogs that we will start to visit in the next talk. So we'll see you then.